All right. So today we are going to talk about the concept of a segmented K-space. So today we are probably not gonna take all the 2-hour slots. So you may think of some of the questions if you have any. So we can you can propose it, and we can try to solve it at the end of this class. Probably today's talk is relatively easy. So we may have some time to do some discussion on the questions. Yes? Okay. All right, so as usual, so for the previous sections that are related to today's topic, the first one is, of course, the concept of K-space. So you can find them in chapter 9, 10, and some in the 13. And of course, the Fourier transform theorem is very important. So you can review them in chapter 11. And also, the sequence we are going to talk about today is mainly the gradient echo sequence. But of course, the same principle will apply to the spin echo. So you can review them in chapter 8 or some of those previous chapters that has the gradient echo and spin echo discussions. So today's content is the first one would be to introduce the segmented K-space concept and related data acquisition strategies associated with this one. And then we are going to introduce the echoplanar imaging technique, which has been very widely used in as a fast imaging method. And also we'll talk about some of the related artifacts that is associated with the segmented K-space and echoplanar imaging. Okay, so let's do some review on the K-space. Let's first take a look at the K-space, 1D K-space scenario. So when we have when we have done a signal excitation, then if we directly collect the signal, we'll be filling the K-space from the center out. So I wonder if any of you can come up and write down the formula for the K-space, for the K-space definition in terms of gradient of the gradient. So as he is writing that formula.
So you mean Kx or Ky?
Just a general. So
this is gradient in whatever direction.
Right.
And this is
Okay. So this is actually one of the specific case where we assume that the gradient is a constant gradient.
Right.
Right. So
if the gradient
if it's
is
not a constant,
yeah, it should be like integral of
all right, a little bit.
yeah.
I have to do that. Okay, very good. Thank you. All right, so we have the same thing here. So if we just directly collect the signal, the FID signal, by applying a radar gradient, actually we are only collecting half the so-called echo. So it's the what we call here is the half fluid acquisition, that we directly start collecting data from the center of the K-space until the edge of the K-space. So as we already know that the center of the K-space contains the information of the global signal, the signal baseline, while the low spatial frequency components, while the edge of the K-space contains the high spatial frequency components. So usually collecting theoretically, we only need to collect half the data would be enough, because the K-space is, in principle, a symmetric space. But practically, we usually we need to go collect the K space from the negative minimum to the positive maximum. So then we will use first we use a pre-phase gradient for the readout, so that we first push the K space to one side, to the negative side or the positive side, and then we use the long readout so that at the center of the readout, the gradient moments would cancel each other out and form an echo, so that we have at the center of the echo we have a zeroed first moment. Oh, sorry, the zeroth moment of the gradients. This is the gradient moment concept we introduced during last section, right? So whenever there is zeroth moment nulling, then there will be an echo. So here is how we collect the K space in the 1D scenario, and here is the representative. Actually, it's the actual echo, gradient echo that we collect from the normal MR experiment. All right, so then we take a look at the 2D K space scenario. Oh, sorry about that. So for the 2D K space, actually we can consider it as just 2D representative of different K space points. So it's just shown in 2D. So in principle, as long as we collect all of these points, then we can be able to give you an image, no matter in what way we collect. So if we have the time, we have the energy, we can do that just by collecting each point using each excitation. Then we can get a very nice image. But usually that's not. That will take too long time. So usually what we do is to do a readout. So each readout collect one line of the K space, and then we do a phase encoding. So each phase encoding, we collect another line of the K space. So in principle, we will be collecting the data in different Cartesian lined style. So here are some of the schemes that we use to collect the 2D K space. So these two on the left, they are the typical Cartesian collecting. So here, this one is the simple gradient echo. We collect each the normal single echo gradient echo sequence, that we collect one line at each sequence. Each excitation. So then we reset the phase encoding, and for the next excitation, we collect another line. And here is what we'll be seeing is the K-space filling scheme for EPI. And also we can also have some of the other K-space collection schemes. Like this is the radial. We just collect a series of readout, but in radial. So here there is no concept of the phase encoding, but it's just a series of rotating readouts. They are all readouts in here. And here is the spiral acquisition. So it's also, there is no phase encoding here. It's just a series of circular readouts. We will be seeing this readout in the last slides. Okay, so for the 3D K-space, so it's the same. The idea is the same. So we have practically to collect a 3D K-space in Cartesian coordinates, we have this readout as each echoes, and then we have 2D phase encoding. So along these two directions, they are all phase encodings. So, and the idea is also to collect all the points, as much point as possible in this 3D K-space. And here is some of the fast 3D K-space acquisition methods. These tools, they are they are both very highly accelerated. So they only collect part of those K-space points, and they do the reconstruction, and they use the redundancy property of the K-space to reconstruct a 3D image. Okay, so in this course, we mainly discuss the Cartesian K-space. So the total scan time of a 3D imaging is basically determined by this equation. Is the TR multiplied by the number of phase encoding steps on both directions, and the number of averaging. So the averaging is usually, if we do not have much time, we usually use one average. If we use more than average, then we can just do the average the images together to improve the SNR. So usually, let's say the N acquisition is 1. So as we discussed during the last section, we can to achieve fast imaging, we have several ways. First one is to reduce TR, as we discussed last session. There will be some steady state signal involved, so we must understand how the signal behave when we are using a very short TR associated with the flip angle and signal spoiling schemes. And then the next step, the other strategy is to reduce the number of the phase encoding steps. So basically, we just the idea is that we just collect part of the K-space instead collecting the whole K-space. So there are several techniques associated with. First is the partial Fourier. The partial Fourier is that we just collect part of the K-space and then just simply zero fill those missing K-space lines. So usually these missing K-space lines are located at the edge of K-space, so that it does not significantly affect the contrast and the signal intensity and the SNR of the images. And then another technique is called parallel imaging. So if you are reading the second edition of the Green Book, the parallel imaging is now the last chapter. So this is a new chapter relative to the old edition. So parallel imaging is also collect just part of those K-space lines, but the idea of this is it will reconstruct those missing lines based on those collected data lines, so that it will give you a full K-space instead of just simply zero filling it. So it also uses the spatial information provided by the phase array coils. So that would be another idea of using the parallel imaging. So parallel imaging is only available if you are using phase array coils, which has several different coil elements. If you only have one coil element of the for the MRI coils, you will not be able to use the parallel imaging. And also another very new technique is called compressed sensing. So I think some of you has been signed with that topic for your presentation, right? Oh, go on. Okay, so the compressed sensing is like a random subsampling of the whole K-space. The idea is that you can use a very small subset of the K-space if you to reconstruct a whole image. If your random subsampling scheme is first is random enough, and second is it has sparse transform domain that you can do. So it's basically like doing the compressing the signal during the data acquisition rather than at the image processing step. Okay, so these techniques, these methods, they the way they reduce the scanning time is by reducing the phase encoding steps. So reducing the data acquisition amount. So another way to reduce the scan time is to increase the data acquisition efficiency. So there are also several methods that is associated with this one. So as I mentioned last time, in industry, usually we call this acceleration in data acquisition. We call this, we use a turbo factor to represent it. So there is, the first one is the case-based segmentation, as we will discuss today, or we can call it a multi-line collection. So the idea is that when we do excitation of the signal, we collect multiple case-based lines rather than only one line. So that the data acquisition efficiency is now improved by the same number of times. And the second one is we can, for some sequence design, we can perform a compact sequence design using the dead times between, for example, the excitation and the signal readout. So this we'll talk more about during next section, which is the sequence design. And also there is this new technique recently that is called multi-band excitation. So as we have seen before, if we do a 2D slice excitation, what do? We just give an RF pulse, we give gradient echo so that we can select a certain bandwidth that is associated with that slice physics. So usually this would only excite one slice. So for the multi-band excitation, is that the RF pulse can excite 3 slices at different locations simultaneously. So that the excitation is simultaneous and then acquisition is also simultaneous. So with the same sequence design and same sequence timing, you actually can acquire the signal from multiple slices rather than just one slice. So this is also a very new development of the current techniques. So actually, I should have put this on as one of the topics for you guys. Okay, so let's also take a further look at how do we fill the case space. So for an MRI sequence, it basically only has 3 kinds of functionalities. The first one is signal excitation. You have to excite the signal. Otherwise, there's nothing for you to collect or manipulate. And then the second important part is the signal manipulation. So what we have seen is, for example, like the immersion recovery, the phase saturation as in water phase separation, spin echo, and the flow compensation, as we will talk about later, and the signal, the spoiler, as we talk about in last section. So all this, there are signal manipulations that you can introduce or manipulate the signal to achieve the signal behavior or signal contrast as you desire. And the third part is the signal readout, right? So even the signal readout, we have different schemes as we saw before. We have this Cartesian readout, we have this radial readout, this spiral readout. So this is also a very interesting topic. So today we are on, mainly focused on the readout part. So okay, so let's first take a look at the single echo acquisition. So when we collect a single phase encoding lines for each RF excitation. So when we are doing this, let's just take a look at this real life sequence design. So I just do a screenshot from the Siemens sequence design too. So this is actually what we are dealing with if we are doing a MRI sequence design. So here we can see that this one, as anyone can tell me, can anyone tell me what this one, or guess what this one is? That's this here. So this RF pulse, what does this one? This is the excitation, I can tell you. So what does this one do before the excitation? You already learned it, should No. So if it's slice left, you should be okay. Let's just it's a little bit small here. So this line is the RF pulse. This is the slice lag pulse. This is the phase encoding pulse gradient, and this is the radar gradient, and this is the ADC. Okay. So what we can see here is we only have RF pulse here. There is no gradients given associated with it.
That's a frequency selective pulse, like to excite just fat or water.
Yes, that's correct. So this one is so when we do not see a gradient associated with it, so usually it is either a non-selective RF pulse or a frequency selective RF pulse. So this one is a fat saturation pulse. So it has the center frequency selected along for the fat instead of the water. So during this RF pulse, it excites the fat signal, and then it gives some strong gradients as spoilers. So it just spoils all those fat signals. And then when you do an excitation for the water, then you can only there's only a water signal left for you to excite. So this is the fat saturation pulse here. Okay, so here is very simple. So we just like a FID sequence, we do an excitation, and then we do phase encoding and the readout pre-phasing, and then we collect the data. So it's simple as that. So for this one is we collect a single phase encoding line for each RF pulse, or more specifically, it's for each excitation pulse. So here means that if we have case space of NY lines, we have it's equivalent that we have divided this case space into NY segments. So this one is actually maximum segmentation scenarios. So is there any question about this one? So it's very clear. So we call this a single echo, and we require the NY excitations to collect the whole case space. All right, so the next one is we collect multiple TE phase encoding lines for each excitation pulse. So we also call this as multiple segment or multiple shot acquisition. So now here we collect, for example, I don't know how many, 1, 2, 3, 4, 5, 6. So here is 11 echo. So we collect 11 phase encoding lines for each excitation pulse. So that means we have improved the signal acquisition efficiency by 11 times. So we know that we have, I wonder if you can see that there is a small blipping here. They are used for the phase encoding. So that means we are collecting different case space lines here, different phase encoding case space lines here. So we are putting them into the same case space, and then we have improved the data acquisition by 11 times. And last is we collect all the phase encoding lines for each RF pulse, for each excitation. So yeah, because I'm just showing this for the demonstration is actually usually if we collect all the phase encoding lines, the echo train length is much longer than this one. So let's just assume that this collects all the K-space line for one at once. So usually we call this techniques is a single shot. So we just collect one image, usually a 1 2D image in one single excitation shot. So this also equivalent to be one segment of the K-space. The whole K-space is one segment. So before we go on, there is some nomenclatures we need to clarify upon. So for the single echo, we have seen that the single echo is that we collect only one echo or one K-space lines for each excitation RF pulse. So that's very simple. And the second one is there is a multi-echo sequence, as we saw before, but there is also a multiple TE sequence. So the main difference between them is that if we mention multi-echo, it may be a little bit ambiguous. So it can all these multiple echoes collected for one during one excitation, they can all go to the same K-space, or they can go to the different K-space. So if they all go to the same K-space, we can call it a multi-echoed segmented imaging. And if it goes to different K-space, so for example, if we collect 11 echoes, because and then we will have 11 K-space lines with different TEs, 11 different TEs. So if we put these different TEs into 11 different K-space to give you an image that is weighted differently, T2 star weighted differently by their TE, right? So it's equivalent to each image is equivalent as a single echo. Is that clear here? Okay, so if we collect, let's just say 5 echoes. 1, 2, 3, 4, 5. 5 echoes. So for the normal multi-echo, we can say that this first echo goes in here, second echo goes in here, third echo goes in here, 4 and 5. So they are all used to fill in the same K-space. So to do this, we need to have some blippings of phase encoding along them. But for multiple TE, there is no phase encoding between them because they are supposed to be collecting the same phase encoded line, but just for different K-space. So where's the? Okay, so whatever. So for the multiple TE, sorry about that. So for the multiple TE, the first one goes here, the second one also goes here, the same phase encoded line. The third one is something like that, so etc. And there's only one phase encoding TE up here. So it decides which the phase encoding for each line, for all these lines. And it goes to different K-space, but the same phase encoding. So it will give you 5 images at the end, which has a different TE. So usually this can be, this type of imaging can be used to do the T2 star mapping because the signal is weighted differently in the T2 stars. So you can do a simple fitting to calculate the T2. So multi-echo and multi-TE, we need to be able to distinguish them. And also a single shot and multi-shot. The single shot is single shot is of course multi-echo one, and then it just give you all collects all the data for the same K space at one time at the same time, and the multi-shot is also equivalent to the segmented K space methods. So sometimes when we will be using all these terms, interleave, differently, but you should be able to tell. So sometimes when we can refer to the same sequence as multi-echo, or it's a multi-shot or segmented, so it's actually the same thing. So what's the pros and cons for doing a multi-echo or segmented K-space strategy to do the imaging? In simple words, we can do a faster scans for high resolution imaging by improving that data acquisition efficiency. But on the other hand, we can do a higher resolution for fast scans if we can reduce the filtering effect caused by the T2 static case. We can see this later. And it depends on whether this is a compromise or an improvement of the current method, so you have to decide. If you want a higher resolution on a faster scans, then it will be an improvement. But if you actually you also already want to have a fast scan, then higher resolution may just be a compromise on this. It just depends on your applications. Okay, so this is a more direct visualization of the acquisition of the segmented K-space. So first, let's take a look at the single echo acquisition. So let's say we have n-wide phase encoding lines. So here is the excitation index. Here we can see there is a different reordering schemes to do this phase encoding. So we can put the first line at the edge of the K-space and then go through the K-space, filling it from top to bottom or from bottom to top. So we call this ascending or descending. We can put the first phase encoding lines in the center of the K-space, and then we do a center out manner to filling those K-space lines, or the center in manner, or we can do a random. The properties of this the single echo acquisition is that, first of all, we have the same TE for all lines. It's basically the same. So everything the same except for the phase encoding. And then we have an infinite bandwidth along phase encoding, because for each phase encoding line, it's a brand new excitation. So it has nothing to do, or we can say it's independent of the signal in previous excitation or the excitation afterwards. But of course, we need to we have to say this if we are doing the SSI or SSSC, right? So if we are doing the steady state coherent, then we will be we cannot claim that there is infinite bandwidth, because the signal is actually from the previous excitations. And this is of course a very long scan time, because we actually need to collect each each K-space line with new excitation. So usually this can give you a very long scan time. If we do it with high resolution, sometimes it can go as high as 20 minutes for a gradient echo. But we can, it can give us a flexible phase encoding reordering scheme. We can collect it in any way we want, even the random, and if in principle it should give you the same image. But sometimes we do need some of this center out or center in method. For example, for some dynamic process. So for example, if we have injected a contrast agent into the blood vessels, and that contrast agent would just decays actually very fast. Its half-life is mainly like 20 minutes. So we want to collect it as soon as the contrast agent is in the bloodstream. So we will collect the center of the K-space at the beginning, where the contrast agent effect is strongest. Right? So that will also depend on. But in principle, for static tissues or static objects, the phase encoding reordering scheme is not a big concern for single echo acquisition. Okay, so the second one is the multi-echo acquisition. So we can all call that this the segmented K-space. So we can see that we have segmented the K-space into, for example, in here it's 5 segments. We have 5 segments here, and if we collect this, we call this is the interleaved segment. So what do we call? Why do we call it an interleaved segments? So for each excitation here, we collect 5 lines. So each lines go to one of these segments. So now we need totally ny over 5 excitation index. So that means this data acquisition efficiency is improved by 5 times. So for each segment, it's equivalent to like a single echo acquisition, right? So for each excitation, each segment gets 1 K-space line, and we can also do the fill each segment using different reordering methods schemes. The ascending, descending, center out or center in, it doesn't matter. So, and as for this segment reordering, we can also have a different reordering schemes. So we can put the first line, the first echo, into the first segment, and the second echo into the second segment in a order in a up to down manner or ascending manner, or we can put the first line into the center segment, and then fill in the segments into inside out, the center out manner. So actually, this segment reordering is very important to showing in determining the image contrast, because for the first echo is always the shortest TE, right? So and for the first echo, for example, it's a little bit longer TE. So the third echo is more T2 star weighted. Now, if we put the third echo into the center segment, that means the whole image is more T2 star weighted. Now, if we put the first echo into the into the center segment, that means the image now is much less T2 star weighted. So this actually is very important in determining the imaging contrast. So of course there is a different TE between different segments, and there is a low bandwidth between the segments because it's collected within the same excitation R pulse. And of course, reduce scan time, as we say in this interleaved segment strategy, we improve the scanning speed by the number of segmentations. So as this is also a segmenting method, if there is a motion related to it, then there might be some phase discrepancies between different segments. So it will also be sensitive to motion. It may create some kind of motion artifacts when we are doing the segmented K-space acquisitions. Okay, so this is another segmented strategy. So it's the simple offset segments. So in here, we only need 5 excitations to collect the whole K-space. So each excitation collects one whole segment. Each excitation collects one whole segment. So in this simple offset segments, we only need 5 rather than ny over 5 number of excitations. So this is actually much faster than the previous scheme. So we can also, so usually we would use EPI-like readout to collect each segment's data. So as we will see later, then for EPI readout, we can only afford to do the ascending and descending reordering for each segment. And the segment order here is not important because for each segment, the signal is totally identical except for the phase encoding, including the TE and stuff. Okay, so is there any question about these two segmented schemes? Okay. All right. So sorry. Right. So finally, is the single shot acquisition. So the single shot acquires the whole K-space just with the one excitation, and then it fills the K-space in this back and forth readout. So the scanline index is basically the same as the single echo one, but it can only afford to be ascending or descending. So first of all is of course different. There is a different TE between different lines, and there is a low bandwidth along the phase encoding direction, and because it's a single shot, so it can give you collect the whole K-space in a very short time. So the typical time of EPI slice is less than 100 milliseconds. And because it's a single shot and a very short scan time, it's very insensitive to motion. All right. Okay, so when we are doing if we do the single shot, then we most likely be talking about echoplanar imaging. So or we call the EPI image. So there are two types of EPI image. The first one is the gradient echo EPI. It directly collects the FID signal that is generated by the excitation pulse. So here is the sequence diagram of the gradient echo EPI. We can see that there is some excitation RF pulse. So we can also see that there are all 3 blips of gradient here. So who can tell me about what their functions are here? So for this one, this is the slide select gradient. So, nope.
At the center of the slice select, it is tend to form that spins dephase. So, in order to rephase, again we apply the negative GSS. area would be half of the total GSM.
Right, that's correct. So yes, this is actually the slide select rephase gradient. So you remember in chapter 16 when we talk about the RF pulse, if we apply the sync pulse, it is assumed that the major effect takes place at the center of the RF pulse. So that means half of this half of this gradient, slide select gradient, it has a dephasing effect on the spin, excited spin. So we need to use negative gradients to compensate this dephasing effect. Okay, so how about this one? This is the readout. So
You need to start from the maximum, minimum negative size of the case.
right, so this is as we have seen in the 1D case-based case. So this is to use to shift the readout to the one side of the KX, and then so that the readout can sweep through the whole K space. And so how about this one?
Same thing.
Yes, it's basically it's the same thing, but it's totally different. So how large? So how do we decide gradient moment for this one here?
It should be the maximum. It should be the maximum.
That depends where we want.
Yeah. Okay. That depends on what?
I mean, from where we want to start, which position we want to move.
Right.
So
Yes. So usually we also, it's the same idea here. We also be able to shift the K space pointer to the one side of the K space, to the edge of the K space along the phase encoding direction. Okay. Right. So another thing is that when we are doing this echo train, we call this echo train. When we're doing this series of readout, we are using the bipolar gradient. So it's the readout gradient, the polarity of the readout gradient is flipped for each neighboring echoes. So this is actually the most efficient way to collect the data, and we just insert a blip of the phase encoding during this run up and run down time, so that this is a very efficient signal acquisition method. Okay, so this is the spin echo EPI, which is also a very widely used sequence. So the difference between spin echo and gradient echo is that it has this 180-degree refocusing, just like a spin echo. So it will generate a spin echo at the TE here, and then we use this whole EPI readout, the same as before, to collect this gradient echo. Oh, sorry, this spin echo. So it's the same here. We also have this phase encoding prephase gradient and this readout prephase gradient. So this sequence is mainly a T2 weighted sequence. Okay, so as we've seen before, we used blip phase encoding between the EPI. So although when we say EPI, we included all this whole sequence diagram here, but most of the time when we talk about EPI, it's more like this readout scheme, that it uses a fast flipping readout gradients along with the blip phase encoding. So we call this is the EPI readout. So it can be used on in different sequences. So in here, we can also call this EPI readout, although it's only 2 echoes. or any multiple echo, we can also call it EPI-like readout. So for this, for any of this EPI-like readout, we use this blip phase encoding so that it can give you a very fast phase encoding. But because it's only very short time, there is only very short time between these two readouts. You cannot go with too high a gradient, or too strong a gradient, or too fast ramping up or ramping down. So usually this is only give you a one blip between the K-space lines. So the readout, and then a blip, and then another readout, and then a blip here. So as we see before, this K-space line, they were acquired differently for the even and odd lines. So for example, for the even lines, it's along, it's sweep through the it's sweep through the KX along one direction, while the odd lines, it will sweep through the KX along the opposite direction. So if there is global field background gradient, or if there is defect in the gradient systems, so it is very likely that there will be a phase difference, a constant phase difference between the even lines and odd lines. So this will create N/2 ghosting. So we can take we can see an example later, but this is a characteristic artifact of EPI. And also, of course, this EPI, if we are talking about the gradient echo, EPI is T2 star weighting. And because during the whole readout train, the signal is decaying along the T2 star, so there is a T2 star filtering effect. So this actually limits, this is actually what limits the resolution for the EPI readouts, because as we in chapter 13 or 14, so we have talked about this filtering effect. So we have if we have a filter along the in the K space, then we will have like a blurring effect in the image domain. So this blurring effect is the limit for the spatial resolution that we can achieve. So even though we can, in theory, we can use a very long readout, but at the end of that readout, there is actually no signal left because the T2 star decays. So you cannot possibly collect any more information for those high spatial frequency components. So basically, that's making the image blurry. So the EPI, the characteristic of EPI first is T2 star or T2 weighted. It depends on which EPI method you are using. And when we collect the EPI, it's usually a 2D imaging. So we usually use a 2D interleaved slice excitation with a relatively long TR. So the idea of doing this is, first one is we use a relatively long TR so that we can avoid the T1 weighting, as we've seen before, right? Steady state is actually a steady state. Incoherent is actually a T1 weighted image. So if we want to collect get a very good T2 star, or mainly T2 star weighting, then we should use a relatively longer TR, so that there is no T1 weighting effect. And for the interleaved slice excitation, that we can, the idea of that is that we can acquire the multiple slice without the slice profile crosstalk. So if do we have eyes here. So usually when we do, for example, this is the head, and we want to do multiple slices. Right, so 1, 2, 3, 4, 5. Okay, so we want to do multiple slices to cover the whole brain, right? So, but if we use the RF pulse, so we hope to get an ideal slice profile, which is the rectangle, right? But due to the limit of the bandwidth we can afford, usually practically we can only obtain a slice like this. So we want to collect the whole brain. So this is one slice, and then the next slice will be something like this. And the third slice, something like this. So we want to cover the whole brain with the slice profile going this way, right? So if we have very close slices positions, and if we collect two slices consecutively, then this one, if we collect this slice immediately after this slice, then this slice would be affected by the crosstalk of this imperfect slice profile here. So usually what we do is we excite the slices in a different manner. So first we excite the slice, the odd slice number, so that we excite this one, and then we excite this one, the third one next, and then the fifth one next, and then at half. So we start 0 here. So starting at half of the TR, we're starting to excite the second slice, floor slice, the odd slice, so that at least this spatially neighboring slices, they were excited with half of the TR apart, so that the signal of the first slice has already decayed, so that it has minimal effect to the second slice. So so usually when we do an EPI, this is the way we do the slice excitation. And also it can also give us some efficient sequence design, so for segmented EPIs. And EPI itself can be single shot or segmented. And the EPI is also compatible with the acceleration methods that we mentioned before, including the parallel imaging, or the readout segmentation, or the segmentation method. But yeah, and what else? Okay, so also most of the time, I think still 90% of the application of EPI, they are done in 2D, because 2D is the most efficient way to do the EPI reading, to do the EPI readouts. But it's sometimes it's also available in 3D. So in 3D is we also do the multiple acquisitions, and we just do partition encoding for each excitation, so that it can give you a 3D excitation. But for 3D, sometimes you can get a higher resolution and higher SNR, because it's 3D is always having a higher SNR than a 2D imaging. But it can also lead to a longer scanning time if you really want to avoid the T1 weighting, and if you want to shorten the scanning time, then you will have a mixed T1 weighting due to the steady state effects. Okay, so when we do the EPI, or when we apply the EPI, we need to consider several factors. first one is it's a readout resolution, or sometimes we call it the sampling rate. So when we do the readout, so we have a series of readouts. And we must keep in mind that the signal is decaying due to T2 star decay, right? So just at some point, this signal is going to decay to zero. So for any other echoes that's collected when the signal has decayed basically down to the noise level, then there's no point in collecting them. So usually we want to design this readout to be short enough to be within the T2 star decay range. So we want to collect this whole, do the data collection within a certain window so that we can still have some signal to collect. So that means we want to squeeze all those echoes into a short time. So that means we also need to use a relatively high bandwidth, high readout bandwidth, so that the sampling rate is very fast for the readout. So usually we use a very the typical readout bandwidth is like 2K, 2000 to 4000 hertz per pixel for EPI. So this is a very high bandwidth. Just because, yes?
Is that why the distortion is worse for EPI?
No, the distortion is high. Yes, that's right. That's right. Yeah. Okay, so for phase encoding resolution, so first of all, as we said, we need to collect all the echoes roughly within the T2 star range. So this would limit the phase encoding lines we can actually collect. And the phase encoding blip, so we usually use the constant blip, which is just shift the K space by one phase encoding, 1 KY. And okay, yeah, the bandwidth here. Okay, so another thing when we talk about is the phase encoding bandwidth. So when we are talking about phase encoding bandwidth, when we are talking about the readout bandwidth, we are talking about the bandwidth that determines the sampling rate between its two readout points. So when we are talking about the phase encoding bandwidth, we are talking about the bandwidth. For example, we are talking about the bandwidth that is between the two neighboring phase encoding points, which are collected by a different readout, right? So, so it's actually this way. So the K space is so this is the KX and this is KY, right? So when we are talking about the readout bandwidth, we are talking about it's related to the sampling rate between two neighboring readout data points. So when we are talking about the bandwidth along the KY, we are talking about the delta time. Delta TSPE. So we are talking about the time interval between the two neighboring points along the phase encoding direction. So, for example, this one here is determined by the interval here, and this 2 is a little bit closer. It's here, so it actually has 2 different. But if we are talking about the center of the echo, usually we talk about the center of the echo. Then it has just has sampling interval that is equal to the readout length, right? So it's equal to the readout length. So the bandwidth of the phase encoding is roughly 1 over the echo spacing, which is the echo spacing. So it's basically the bandwidth of the readout divided by the number of readout sampling points. So that means the phase encoding bandwidth is NRO times smaller than the readout bandwidth for EPI. So that means it's much lower. For example, if we have collected like 2000 hertz per pixel along the readout, and we are collecting like let's say for 100 sampling along the readout, then we only have like it's only about like 20 hertz per pixel. So it's actually a very low bandwidth. So that means any field inhomogeneity or any chemical shift caused like the fat and water, it can have a very significant effect along the phase encoding direction.
So if the distortion is worse in the phase encoding direction, we should reverse it by, we should change it by the frequency encoding, right? If in EPI we have severe distortion in the phase encoding, that's because of the very low bandwidth, right?
That's right.
So we can replace it, or we can change it with the frequency encoding direction, right?
Yeah, but it's this.
To get rid of that severe distortion.
You cannot, because as long as you collect a series of echoes, this is what you get. Just by simply changing the direction doesn't change the phase encoding bandwidth, right? The phase encoding bandwidth is still this low. So if you just change the readout to the phase then we should not be calling that. How do we say? If we just change the field of view by rotating it so that the new readout is along the original phase encoding, then the original readout is now the phase encoding. So there is still this and the same distortion, the same chemical shift along that direction.
Not in the previous direction, right?
Mm-hmm.
Not in the first direction.
Yeah, not in the first direction.
So my question is that if we have severe distortion in one specific direction,
Mm-hmm.
we can get rid of this by changing
Yes, but if that only takes place along that one direction, and you know that for sure it won't take place if we just rotate that field of view. But most likely it will still take place just along the different directions. Yeah. So the scanning speed is very fast. As we said before, it collects one whole slice in less than 100 milliseconds. So practically we can collect on like 30 to 35 slices in 2 seconds. So this is a very fast imaging method. And also there's when we talk about the EPI, we need to show some concern on the safety. So it has a very loud noise. Actually, it's a very high-pitched noise. You can hear them during next section. So The noise is because we have very high bandwidth of the readout, so the fast switching of the gradients create the noise, and also the vibration, and also the neural stimulation, because very fast switching gradient would induce the active current in your muscles. So those active currents would actually make your muscle twitch. So. Right, so here is some images and artifacts. So SS here means single shot. So it's single shot EPI. Here as this is the gradient echo EPI, and this is spin echo EPI. So from here we can see it's the same slice location, exactly the same. So we can see that for the gradient EPI, we can see that there is a lot of signal dropouts. Some distortions if we look at the eyeballs, when compared with the spin echo, because spin echo can refocus those few inhomogeneity induced phase dispersions, so it can refocus those signal dropouts caused by the field inhomogeneity. So we can see that we can actually see some of it can actually recover some of those signals that is inside, for example, the sinus and ear canal, and it can give you a much higher signal intensity. But in here, this one is the gradient. The gradient echo EPI is a T2 star weighted. So as we have, some of you might know that the T2 star weighted image is very good for doing the fMRI study. But also T2 weighted image can also do fMRI study. So this is the comparison of the fMRI results. So here is the subject was looking at flashing checkerboard. So we can see that the gradient echo EPI can give you much stronger activations in the visual cortex, while the spin echo EPI can give you smaller activation, but it's supposedly to be more localized. So there are, different pros and cons for both methods. Also, EPI can be used for diffusion weighted image or diffusion tensor imaging. So for diffusion weighted, it is basically we are talking about the spin echo EPI, because the diffusion weighted module itself is a spin echoed module. It requires some requires the use of refocusing our pulse. So we can see that this is the diffusion weighted image if we along different directions. So we can see that diffusion induce signal loss in different directions, and using this directional diffusion information, we can calculate the Y matter tracks and do the Y matter tractography to show how the Y matter in your brain looks like. So here is the N/2 ghosting. So this is specifically related to EPI. We can see that the whole object is splitted in two and then shifted exactly by 1/2 of the FOV. So this is caused by the phase discrepancy between the even and odd lines. And also, although the EPI is a very fast imaging, it still requires like 100 milliseconds to acquire the data. So if there is strong enough motion during this 100 milliseconds, which is still possible, then we can still see some motion artifacts. But this is a relatively rare case. Usually the subject can keep very still, and we can get some perfect images like this. And also the chemical shift artifact. So this is chemical shift. We can see that the center one is the oil, and the ring is composed of water. So we can see that there is a relative spatial shift of the fat signal. So this is when you see this chemical shift artifact, you can know that it must be along the which direction? Huh? No, the phase encoding direction. Yeah, because it has this very low bandwidth. So, for example, if at 3 Tesla, the chemical shift between water and fat is like 4.5 ppm. So it's equivalent for like 1600 hertz at 3 Tesla. So if we have 20 hertz per pixel bandwidth along the phase encoding direction, so the delta Y is 60 divided by equal to 23 pixels. So that means the fat signal would have shifted by 23 pixels along the phase encoding direction if the phase encoding bandwidth is like 20 hertz per pixel.
So is that different from a normal gradient echo image? Isn't it usually in the frequency encoding direction that you see the chemical?
Right, but for the normal gradient echo imaging, as we said before, it is in coherent steady state. So that means each excitation, the signal from each excitation is totally independent from the one that is before. So this is equivalent to an infinite bandwidth along the phase encoding. So for infinite bandwidth, there is no chemical shift related shift. Okay, so there are just some alternate forms of EPI. So it can some people to try to acquire even faster EPI scans, so they collect the data during the run up and run down times. There is a segmented EPI, so we can collect the EPI in the two segmented schemes we mentioned before, because just we said before, there is T2 star decade, so we would like to collect the whole, have the whole readout trained within the T2 star range. So by doing this segmented EPI, we can actually shorten the readout train, so that we can easily do that and achieve a higher resolution, so that the resolution is not limited by the T2 star filtering effect. And there is also an angled case-based EPI, segmented EPI with oscillating gradients, and spiral readout EPI. The spiral readout EPI is another more popular form of Schottky EPI, as we can see a little bit more later. So a quick summary of EPI. There's a pros and cons. So if we want to collect a very fast image, then we need to sacrifice some of the spatial resolution. So usually if we use the EPI to do the fMRI, we actually use very low spatial resolution. Like the case-based matrix is usually like 64 by 64 for the whole brain. This is equivalent to like 4 millimeter of the voxel, for the voxels. So this is a very coarse of the signal, but it can give us a very fast temporal resolution, so that we can collect different time points to capture the activity of the brain. And also for EPI, we use EPI mainly because it's T2 star weighting. But for the T2 star weighting, it is also very susceptible to susceptibility artifacts. For just like we see before, that the signal dropouts near the sinus, the air tissue boundaries. So this is what we need to make a compromise between these two things. We will need to use sufficient T2 star weighting, and while we can avoid a serious susceptibility artifacts. And also for SNR and distortion, if we want to use higher SNR, then the distortion may be, stronger due to the bandwidth-related tissues. Okay, so for those applications that mainly use the EPI, the first one is the functional fMRI. The second one is like the perfusion. We can detect how the blood is perfused into the blood tissues. So these methods would include arterial spleen labeling and contrast-enhanced perfusion weighted imaging, and also the diffusion, as we just saw. Okay, so come back to the segmented case space. There are several artifact and correction methods is required if we want to collect a good case space, because when we collect the case space in different excitations, there is always a possibility that the phase between these different excitations, the signal of the phase of the signal collected at different excitation would be affected by the background gradients or some other sources. So here is some of the phase error sources. First one is the global background gradients. It would lead to a case space shift. So the solution is that we can collect some navigator phase and do some extensive phase correction. And then there's another phase chemical shift. So it will lead to the water-fat, relative shift. So the solution usually is we do a fat saturation to remove the fat signal. And also the eddy current, because we use very high bandwidth, we use very fast, switching readout gradients. So it can lead to an eddy current to create sort of geometric distortion, so that the image is distorted. The solution is that we can use, for example, segmented EPI to reduce the echo train length, so that eddy current effect is less, and the T2 star decay related to the eddy current is also less. So the rule of thumb is that the shorter the echo train length, the less the signal distortion, the less the image distortion will be. And also there is a motion. The motion would be will cause some kind of ghosting artifact. So the solution is either we can use head fixation. So we fix the head, or we fix the body part, so that there is a limited motion. And also we can also use the navigator method to do the phase correction. Okay, so here is what's shown if we collect the EPI in the simple shift segmented case space. So we can see that for different segments, there can be some kind of phase difference, which would be will lead to ghosting artifacts. So there is a quick question for you. What is the difference between this segmented phase error and EPI's N/2 artifact? So you can think about that. Okay, so the last part, we can take a look at spin echo based segmented acquisition. So it's very similar, just also it's multi-echo, spin echo sequence. It's just simply that. So usually we call this as fast spin echo or turbo spin echo. So all those segmented schemes that we mentioned before is also applicable to the spin echo. So the concern of this one is usually when we do the spin echo experiment, we want to get some good T2 weighted and limited T1 weighted. So usually the scan time is still a little bit longer for spin echo based acquisitions than the gradient echo based acquisitions, even with the segmented or multi-echoed method. And also for spin echo, there is this SAR concern, which is the power deposition of the RF pulse power into the human body. So, and also T2 decay is the same idea, the filtering effect, right? So segmented acquisition can also help to improve all these issues. And it's with a spin echo or this fast spin echo, multi-echo spin echo sequence, we can afford to use more flexible reordering schemes because the phase encoding is actually done during each interval between the refocusing pulses. So we can see that phase encoding is encoded and then refocused. So this gives us a more flexible reordering schemes due to the flexible phase encoding gradient table. So by doing a different reordering using the same fast spin echo, we can actually get different image contrast like photon density or T1 weighted or T2 weighted, all using basically the same structures except for the gradient encoding schemes. But of course, we need to, when we are talking about the turbo spin echo, we need to use the so-called CPMG design or the variable flip angle. But this is, if you are interested, you should take a look into these topics. Okay, so finally is the let's briefly mention the spiral acquisition for the EPI. So the spiral acquisition is we just use this oscillating gradients. They both actually formed one single readout. So this one single readout fills the K space in a spiral manner. We can collect this spiral from inside out, or we can also collect the spiral from outside in. So this is a single shot spiral, and this is a multi-shot spiral. So using the spiral acquisition, you can give you a very smooth gradient changes. So relatively, it gives you a less requirement for the gradient systems, and it can also give you a less eddy currents, and it can afford a very short TE. So if we collect Cartesian echo trained, so usually because due to the blipping phase encoding, right? So usually we have to collect the center of the K space in the center of the echo train. So that means we cannot use a very short TE. But using the spiral acquisition, we can actually we collect the center of the K space just immediately right after the excitation. So it can give you a very short TE, and it can give you a very fast scan, even for very high resolution. So because this is actually just a continuous acquisition of the whole K space in one single shot. So it can be, sometimes it can even be faster than the normal EPI. And it can, it is also comfortable for segmented acquisition so that we can collect much higher resolution imaging. All right, so this is a revisit of the SNR concept. The relation of between different parameters and signal to noise. So when we are talking about this segmented acquisition, actually, in principle, when we use segmented acquisition, we do not change any of these parameters that can potentially affect the SNR, right? We are still collecting, in principle, we are still collecting the same phase encoding lines, the same number of phase encoding lines, yes. And but the total imaging time, of course, is reduced. So if we do not take into account of the T2 or T2 star decay, then doing the segmented or multi-echo acquisition should give you the same SNR. So that means, but you can collect the data with a fraction of the time. So this is a very good, from a SNR point of view, it's just very good to do segmented acquisition. All right, so yeah, this is the homework for this section, and for the next session, we'll talk about chapter 20. Right. Okay. So, is there any other questions?
I have a little bit practical question.
Mm-hmm.
We ran a PGI experiment on 70.
Yep.
The SNR was not in the order that we would like to be, so we increased the voxel size at the first step and then increased the number of acquisitions, but it is not satisfactory in the SNR. Is there any other way that we can increase the SNR?
Well, for diffusion weighted, it's actually the SNR itself is.
I'm asking this because I understood that the sequence is like the gradient echo EPI.
No, it's spin echo EPI.
You sure it is a spin echo?
Yes, I'm sure. I'm pretty sure.
Yeah,
Everybody
is saying that this is a gradient.
No, it's actually a spin echo EPI.
Okay.
Yeah. So
this is
yeah, but
maximum.
for diffusion weighted image, actually, if we go back to take a look at that, for diffusion weighted image, low SNR is usually what it is. It usually will give you a low SNR because the use of the diffusion weighted gradient. So, and if you are doing at 70, that means you are actually using a very small voxels. Although you say that you have increased the voxel size, it's still very small. So yeah, so yeah, I don't think there's, and also depending on how the strength of the diffusion weighting you are using.
It's 2000.
Yeah, 2000 is actually a very high diffusion weighting. So yeah, so yeah, apart from the doing more averages, I think that's not much you can do.
The number of averages to 24.
Mm.
So
Still not good.
not practical.
Yeah, well, that that may have many different reasons, and we may need to I will need to take a look at the images before I can say anything. But
one of our homework problems, they said that if you took a very fine, just pretty much unrelated to this, you had a very fine, narrow radio frequency pulse, you could just excite fat or water. And then they said that there was a problem where you had silicon added to the fat and the water, and what you wanted to do is null fat and water to get an image of silicon.
right.
Why would, if you couldn't have these fine pulses, why not just excite silicon to begin with and
Yeah, the problem is that spectrally selective RF pulse is actually not that fine in the spectrum. So, actually, we've done this test. We want to suppress the fat in the eye. Actually, we found that using a normal fat saturation pulse, I actually suppress all the blood vessels even those from the internal cerebral arteries. So that means it's spectral. So let's say this is fat, and this is like water. So that means the spectral bandwidth of the RF pulse is actually quite wide. So it affects the water signal. So I'm not sure where the silicon sit. Is it between the
It was
It's left to the
to
fat.
the left.
left of the fat? Okay, yeah. But if you want to suppress this too, I think you can easily do that. But if you just only want to suppress the silicon, then it may be a little bit difficult. Not with this saturation, spectral saturation pulse. Yeah. Okay. So yeah, if you have any questions, we can just discuss after the class. All right. Okay. Thank you.